In 6.1, we're obviously starting Chapter 6, and we're going to start with the concept of a sampling distribution. So first of all, we need to write down a couple definitions. You need to know what a statistic is and what a parameter is. So pause the video and write down these definitions. So a statistic is a number that describes some characteristic of a sample. Now, statistics could be a mean, it could be a median, it could be a standard deviation, it could be range. All these different measurements that represent a sample is called a statistic. Now, if we use those same measurements to represent the entire population, it's the entire thing, then that's called a parameter. All right, so you got to remember these very, very carefully. S and P. Statistics come from samples, so the S's go together. Parameters come from populations. So you need to know these symbols down here. Learn these symbols, okay? So if I say mu, that's the population mean. That's the average of the entire population. But if I say X bar, that's the average of just a sample of the population. So a population of all students at a school, a sample is just those in one class. Okay? All right, P is a population proportion. So this goes with like the whole idea of categorical variables, like what proportion of the students are male. P hat is a proportion, but it's a proportion of only a sample. What proportion of males, or what proportion of the students in my class are males? Okay, class is a sample of the whole population. So we differentiate it with a little hat on it. So P hat. Sigma is the population standard deviation, which we've talked about before. So if we take a sample and then find the standard deviation in the sample, we use the symbol little s. So it's really important that you learn these symbols. So you may want to pause the video and write these down. All right, so the process of statistical inference involves using information from a sample to draw conclusions about a wider population, because reality is you'll never get every single person in the population to respond or be able to survey every single whatever of a population. It's not possible, but what you can do is get a sample. And so that's what this diagram is showing you, is it's possible to get data from a sample. And we can, if we make a good sample, if we pick a good sample that represents a population, then we can make inferences about the population. So we collect data from the representative sample, and then from that sample we make an inference about the big population around it. Okay? So that's the whole idea of sampling distribution and statistical inference. That's where we're trying to go here in stats. But we have to do it with samples, not the whole population. So we do something called a sampling distribution. It's a sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the population. All right, so a lot of busy words, okay? But here's what I want to say. It's all possible samples of the same size from a population. So if I'm looking at all the students at Richland High School, if I take a sample of 10 students, that's saying I get every single possible sample of 10 students from the whole population of Richland. Difficult to do, but it's easier to get 10 than it is to get everybody. So remember that a distribution describes the possible values of a variable and how often these values occur. Now that variable, all these different measures that we've talked about, mean, could be mean, median, standard deviation, it could be range. Any of these different calculations could be collected. All right, so I could find the mean from every single sample of 10, and that would give me a better idea what's going to happen in the population. So let's keep going. I know it's a little cryptic. Let's just keep going. So here's the first example. Identify the population, the parameter, the sample, and the statistic in the given setting. All right, this is just vocabulary and symbols. Make sure you use correct symbols. From a large group of people who signed a card saying they intended to quit smoking, a random sample of 1,000 people was selected. It turned out that only 210, which is 21% of the sampled individuals, had not smoked over the last 6 months. All right, so notice they gave me a percentage. Okay, that's a clue that this is a proportion. Percents and proportions interchangeable here. Okay, so let's look at this. What is the population we looked at? Okay, a large group of people who signed a card to they quit smoking. So they're trying to figure out about all the population, all the people who signed the card saying they intended to quit smoking. Okay, that is the population we're trying to predict from. Okay, we want to know about these people, all of them, but we know we're not going to get a hold of every single one of them. All right, so that's our population. Our sample is the 1,000 people, 1,000 random people selected. Okay, that's a sample. So then let's find the parameter. What is the parameter we're looking for? What parameter? What are we trying to predict about the population? What measurement are we looking for? So we are looking for parameter. We are looking for the true proportion. What really we want to know? What is the real proportion of all the people? What is the true proportion of the population who quit smoking? Okay. The statistic is the measurement that we took from the sample. Okay, well, what do we get from the sample? We've got a 21%. Okay, the proportion of the sample who quit smoking. 21% of the sample quit smoking. All right, so you got to find those 4 things from each scenario. Identify the population, the parameter we're measuring, the sample, and the statistic. So let's look at B. A pediatrician who wants to know the 70th percentile for the distribution of heights of 10-year-old boys. So she selects a sample of 50 10-year-old male patients and calculates that the 75th percentile in the sample is 56 inches. All right, so let's think, what's our population here? She wants to know about the heights of 10-year-old boys. 10-year-old boys. Okay, and what's the parameter we're trying to predict? He wants to know the 75th percentile for the distribution of height of 10-year-old boys. Okay, now this sample, what is the sample she took? Well, if you read it, she had 50 10-year-old boys, and the statistic that she got, she found that the 75th percentile of her sample was 56 inches. All right, so again, find those 4 things: population, parameter, sample, and statistic from the given situations. Now, let's look at number 2. Given the population of 2 male students and 3 female students, along with their quiz scores, here it is. List all 10 possible simple random sample of size 2. All right, so let's do this part first. List all 10 samples. Okay, so we have Abigail and Bobby, Abigail and Carlos, Abigail and Deanna, Abigail and Emily. We have Bobby and Carlos, Bobby and Deanna, Bobby and Emily. And we have Carlos and Deanna, Carlos and Emily, and then we have Deanna and Emily. Good. So those are our 10 possible sample sizes of 2. Okay. Now, then it says calculate the mean quiz score for each sample. Well, okay, A and B would be 10 plus 5 divided by 2 gives me 7.5. All right, so what I'm doing is averaging the different combinations, like Abigail and Carlos. 10 plus 10 is 20, divided by 2 gave me 10. Then I did Abigail plus Deanna. 10 plus 7 is 17, divided by 2 is 8.5, and so on and so forth, until I've covered all 10 different samples of size 2 and found the averages of each of those samples. Once I know that, I can move on to the next step for the dot plot. Then it says display the sampling distribution of the sample mean on a dot plot. Okay, so let's create a dot plot. Sample mean quiz scores with a sample size of 2, n equals 2. All right, so look at our range here. Lowest one was 6, and the highest is 10. So we'll go 6, 6.5, 7, 7.5, 8, 8.5, 9, 9.5, 10. All right, and then you put dots where the dots go. So I put 7.5, and then I put 10, and then I put 8.5, and 9.5, and 7.5, and 6, and then 7, and then 8.5, 9.5, and then 8. All right, so that's what you have to do. Find all the combinations of 2, find the means of those combinations, but make a dot plot. So each one of these dots represents one sample mean. Okay, one sample mean. All right, so make sure you label your dot plot and make it clear. Number 3. All right, lots of words, so listen carefully. A school newspaper article claims that 60% of students at a large high school completed their assigned homework last week. Some statistics students want to investigate if this is true, so they chose a simple random sample of 100 students from the school to interview. When they found that only 45 of the 100 students completed their homework last week, they suspected that the proportion of all students who completed their assigned homework last week was less than 60%, claimed by the newspaper. To determine if a sample proportion of p hat is of 0.445 provides convincing evidence that the true proportion is less than p equals 0.6. The class simulated 250 simple random sample of size 100 from a population in which p is equal to 60. Here's the results. All right, so what did they do? They took 250 different samples of size 100 each, and they found out what's the proportion in those 100 of students who did their homework. All right, so look at this dot plot. Each of these dots represents one sample proportion, like one proportion measured from one sample of 100 students. All right, so let's think about this. There's one dot on the graph at 0.73. Okay, right there. Explain what this dot represents. Okay, what does it represent? It represents in one simple random sample of n equals 100, represents 73 students out of those hundreds, or out of that 100. 73 students did all the assigned homework. That's what one dot represents, one sample size 100, and its result. Okay. B. Would it be surprising to get a sample proportion of 0.45 or less in a simple random sample size 100 when p is equal to 60? Explain. Look at the dot plot. Okay, 0.45 is really low compared to all of our other results. Here's 0.45. Do we have any dots over here at all? There's nothing there. So if I make a boundary of this right here, do I have anything there? So would it be surprising to get a sample of 0.45 or less? Yes. Okay. And you would justify this by saying in the 250 samples, size 100, none of them had a sample portion of 0.45 or less. Okay, that's all you have to tell me. How do you know it would be surprising? Well, because none of them did. In 250 replications of the same thing, none of them had anything that low. All right, C, based on your answer in part B, is there convincing evidence the proportion of all students who completed their assigned homework last week was less than 0.60? Is it less than that? All right. So we got they got a 0.45 in their sample. So what are the chances of that? That's what they're saying. Well, we just set up here in part B that there's a 0% chance of happening based on our 250 samples. It happens 0 times, right? So if you remember back when we were first analyzing if is something surprising, we would say if the probability of it was less than 0.05, then that would be surprising, right? It's less than 5% chance of happening. Now, another phrase we use in the same vein is convincing evidence. If it's less than 5% chance of happening, then that is convincing evidence that something happened. Well, in this case, that's convincing evidence that the percent of all students who complete their homework is really less than 0.6. So that's what we're getting at here. So we would say yes. Because 0% is less than 5%, we have convincing evidence that the true proportion of students who complete their homework is less than 0.60. Okay? That's all you have to say. And this is your reasoning because 0 is less than 5%. All right, I know that's a technical problem. We'll talk more about it when we get in class.